Double integrals over polar regions. We're going to start by looking at what's called a simple polar region. This is a region in the Cartesian coordinate plane that's trapped between two rays, theta equals alpha and theta equals beta, where alpha and beta are real numbers, and also trapped between two functions of theta, r equals r1 of theta and r equals r2 of theta. Here, r and theta are the polar coordinates of a given point in the plane. We see our region here in yellow. And if we want to do a double integral over this region of fr theta dA, we could change this to an iterated integral in terms of r and theta by letting the outer integral, the theta integral, go from alpha to beta, and the r integral to go from the function r1 of theta to the function r2 of theta. And notice that the integrand inside of the double integral, we have the same function, f of r theta, but there's an extra factor of r that appears. This always happens when we change from a double integral to an iterated integral in polar. Always remember to put in that extra factor of r. Now, I want to look at a couple of special cases of this that occur pretty frequently. One is when the shaded region goes all the way into the origin, like in this second picture here. In this case, r1 of theta is just 0. So our iterated integral has a 0 as the lower limit on the inner integral, the r integral. It's nice to remember that if the region touches the origin, then that lower limit will always be 0. Another special case is when beta is equal to alpha plus 2 pi. In this case, the integral is going from alpha to alpha plus 2 pi. And once again, since the region touches the origin, the lower limit of the inner integral is 0. In most cases, when we have a picture like this, we'll just set alpha to 0, and the outer integral will be going from 0 to 2 pi. But we could start from any real number alpha as the lower limit and add 2 pi to that for the upper limit. Let's look at an example. Go ahead and pause the video, try this example yourself, and then resume the video to check your answer with mine. Evaluate the double integral over the region R cosine theta dA, where R is the region in the first quadrant outside the circle R equals 2 and inside the cardioid R equals 2 times 1 plus sine theta. As always, we want to start by drawing a picture. The circle is pretty easy to draw. In polar, the equation R equals 2 has a graph that is a circle of radius 2 centered at the origin. For the cardioid, I'm going to make a little table of values. So I'm going to pick some key values for theta and substitute them in to get the corresponding values for R. So starting with theta equals 0, we get R equals 2 times 1 plus sine of 0. Now the sine of 0 is 0, so we just get 2 times 1, which is 2. The next easy key point would be theta equals pi over 2. Since the sine of pi over 2 is 1, and 1 plus 1 is 2, we get R equals 2 times 2, which is 4. The next key point would be theta equals pi. The sine of pi is also 0, so once again we get R equals 2 times 1, which is 2. The next key point would be 3 pi over 2. The sine of 3 pi over 2 is negative 1, so we get 2 times 1 plus negative 1, or 2 times 0, which is just 0. Let's also do 2 pi, and the sine of 2 pi is the same as the sine of 0, so we simply get 2 again. So let's plot those key points. The point 0, 2 means we make an angle of 0 radians with the positive x-axis, meaning we're lying along the positive x-axis, and R being 2 means we go out 2 units along the positive x-axis. You could see that point plotted there at the right-hand side of the circle at 2 on the x-axis. What about the point pi over 2 comma 4? So when theta is pi over 2, that means we're along the positive y-axis because we're pi over 2 radians away from the x-axis. So we go 4 units along the y-axis. For theta equals pi, we're now along the negative x-axis. And again, we have to go 2 units in that direction. So we see that we have that leftmost point that touches the circle there. At 3 pi over 2, we have 0. So whenever r is 0, that is always just the origin. So we're coming into the origin there. And theta equals 2 pi and r equals 2 is the same point we started with. So now how do we actually draw this cardioid? Well, we sweep out arcs from one point to the next. So from the first point, 0, 2, that rightmost point, we sweep out an arc until we hit the point pi over 2, 4, the uppermost point. And then we sweep out another arc from there to the point pi comma 2, which is the leftmost point there. And then notice how we sweep out an arc as we travel from pi 2 to 3 pi over 2, and again from 3 pi over 2 to 2 pi. So the region that we're looking at is this shaded yellow region here. Notice it's only in the first quadrant. It's outside the circle and inside the cardioid. So now we want to evaluate the integral. Now, first, remember, when we're setting up our limits, that theta is going to be going between 0 and pi over 2, because we're just in the first quadrant there. And I drew a little arrow there to show how the inner integral is going to work. It's going to go from the inner curve to the outer curve. That's how integrals in polar work. So we're going from the circle r equals 2 out until we hit r equals 2 times 1 plus sine theta. So when we set up the iterated integral, the theta limits are going from 0 to pi over 2, and the r limits are going from 2 to 2 times 1 plus sine theta. And inside the double integral, the integrand, we have cosine theta. And don't forget to throw in that extra factor of r, as we always do whenever we change to an iterated polar integral. So we're doing the r integral first, and that's just a power rule, r squared over 2. So we get 1/2 r squared from 2 to 2 times 1 plus sine theta. Cosine theta just sits there as a constant because we're integrating with respect to r and not with respect to theta. So I'm pulling the 1/2 outside of the integral because it's a constant, and plugging in the upper limit, we get 2 squared, which is 4, times 1 plus sine theta squared, cosine theta. And then plugging in the lower limit, we just get 4 times cosine theta. And as always, we subtract those two. Now, integrating with respect to theta, for the left term, we could just do a little substitution. If we think of u equals 1 plus sine theta, then du is cosine theta d theta. So that just becomes 1 plus sine theta cubed over 3. The 4 I took out and multiplied by the half to get 2 over there. And for the rightmost term, cosine theta just becomes sine theta. And that's going from 0 to pi over 2. Now, when we plug in the pi over 2, well, the sine of pi over 2 is 1, so we get 2 cubed over 3, which is 8/3, minus sine of pi over 2 again is again minus 1. And then when we plug in the 0, the sine of 0 is 0, so we just get 1 cubed over 3, which is 1/3, and the right term goes away because the sine of 0 is 0. Combining all that gives us a final answer of 8/3. Let's try another one. Go ahead and try this yourself. As a hint, notice that this is a double integral being done as a type 1 region, and you want to change it to an iterated integral that reflects a polar region. Go ahead and pause the video, try this yourself, and then resume the video to check your answer with mine. Okay, so we want to evaluate the double integral 0 to 2 x to root 8 minus x squared of 1 over 5 plus x squared plus y squared dy dx. As always, we're going to draw a picture first. The lower limit of the integral is x, so we have y equals x. For y equals the square root of 8 minus x squared, just to see what that looks like, let's square both sides of that equation. So we get y squared equals 8 minus x squared. Adding the x squared over, we have x squared plus y squared equals 8. And you might recognize that as a circle of radius root 8. But it's only the upper half of the circle, because if you go back to the beginning, notice we only have the positive square root and not the negative square root. So we draw here a semicircle, the upper half of a circle of radius root 8. So the radius is a little bit less than 3. Luckily, those two curves intersect at the point 2, 2. To see that, notice that for the point 2, 2, y is in fact equal to x, so it lies on the line. And 2 squared plus 2 squared is 4 plus 4, which is 8, so it also lies on the circle. If you don't see that right away, you could solve the system of equations x squared plus y squared equals 8 and y equals x formally to figure that out. So the shaded region is here. Notice that x is going from 0 to 2, and then y is going from the lower curve, y equals x, to the upper curve, y equals the square root of 8 minus x squared. The equation y equals x in polar is given by theta equals pi over 4. Notice that that line is making an angle of pi over 4 with the positive x-axis. The equation x squared plus y squared equals 8 in polar is r squared equals 8, because x squared plus y squared is equal to r squared. So we could rewrite that as r equals the square root of 8. So again, the equation of the line in polar is theta equals pi over 4, and the equation of the circle in polar is r equals root 8. So now we could change the integral into an iterated integral in polar. The theta limits are going from theta equals pi over 4 to theta equals pi over 2 being the positive y-axis. And r is going from 0 to root 8. Notice that it starts at 0 because the region touches the origin, and it goes to the equation r equals root 8, which is the equation of the circle. Also, we replaced x squared plus y squared inside the double integral by r squared. So we have a 5 plus r squared in the denominator there. And don't forget to multiply by a factor of r. I just put that in the numerator. We always do that whenever we change to a polar double integral. So we'll do this one with a simple substitution. If we let u equal 5 plus r squared, then du is 2r dr. The 2 is missing, so I'll go ahead and put that in, and I'll make up for that by multiplying by 1/2 on the outside. So we get 1/2. And we have du over u, which becomes ln of u. I'll just change that back right away to ln of 5 plus r squared, and that's going from 0 to root 8. So plugging in the root 8 squared is 8, 5 plus 8 is 13, so we get the ln of 13. And when we plug in the 0, we get the ln of 5, which we could write as ln of 13 over 5 using the basic difference rule for logarithms. And since everything is constant with respect to theta, we just get theta from pi over 4 to pi over 2. So we get pi over 2 minus pi over 4, leaving the constant out front. So pi over 2 minus pi over 4 is pi over 4. Multiplying that times 1/2, we get pi over 8. And we still have ln 13 over 5. Let's do one more example. Find the area enclosed by the 3-petal rows r equals sine 3 theta. Once again, go ahead and pause the video, try this yourself, and then resume the video to check your answer against mine. Let's start by drawing a picture of the 3-petal rows, starting with a table of values. Notice in this case that for my key points that I'm using for theta, I'm not just going to go from 0 to pi over 2 because I'm missing too much information. Instead, I want to set 3 theta equal to pi over 2. And when we divide by 3, we get theta equals pi over 6. So we want to move in multiples of pi over 6 instead of multiples of pi over 2 so we don't lose too much information. So when theta is 0, well, the sign of 0 is just 0. So we get r equals 0. When theta is pi over 6, we get the sine of 3 pi over 6, or the sine of pi over 2. Again, that's why I chose the pi over 6, so that the pi over 2 would come out next. And the sine of pi over 2 is 1. So we get a 1 there. When we plug in a pi over 3 for theta, we get the sine of pi, which is 0. When we plug in a pi over 2 for theta, we get the sine of 3 pi over 2, which is -1. Then next 2 pi over 3, we get the sine of 2 pi, which again is 0. The sine of 3 times 5 pi over 6 gives us the sine of 5 pi over 2, which is the same as the sine of pi over 2, which is 1. And finally, the sine of 3 pi is just 0. Okay, so that gives us a nice table of values for which we could start drawing our sketch. And if we sketch this, we'll see that we get this three petal rows shown here. Now notice that the first time that this rose goes back to 0 is at pi over 3. You can see that clearly in the table. When theta is 0, r is 0. And then when theta is pi over 3, that's the first time that r becomes 0 again. So in other words, theta equals pi over 3 is a ray that is tangent to that three petal rose as shown in the picture there. So now we're ready to compute the double integral over r dA. Remember from the last lesson that that's one way to compute the area of a region, by taking the double integral over the region dA with nothing inside the integral, which again means there's a hidden 1 inside the integral. Geometrically, that gives us the area of the region. So I just want to mention something important here. If you look at in the middle of this table, there's a negative r value. If we start doing this double integral and we travel through negative r values, then the actual value we get is not going to be equal to the area, because the negative r values are going to cancel with the positive r values. So one way to avoid that is to split up the integral into pieces, so that we're just handling the positive parts and the negative parts separately, and then taking the absolute values and adding them up to get the full area. But in this case, we could do something simpler. Because this picture is symmetrical, we can just take the area of one petal of the rose and then multiply it by 3 to get the full area. That's an easier way to do it, so we'll do it that way. So I'm just going to look at this first petal in the first quadrant and set up an iterated integral to do that. We're going to take the integral only from 0 to pi over 3, because again, theta equals pi over 3 closes out that first petal of the rose. And then we're going to go from 0 to sine 3 theta, right? It starts at 0 because the region is touching the origin, and it goes out until we hit the curve, which is r equals sine 3 theta. Don't forget to put that factor of r inside the iterated integral. And then we're going to multiply this by 3 because we want the area of the whole rose, not just one of the petals. So the inner integral is pretty simple. It's just a power rule, r squared over 2 from 0 to sine 3 theta. Substituting in sine 3 theta for r, we get sine squared 3 theta. I pulled out the 2 so that we have a constant of 3/2 outside. Now we're going to need to use one of our power reducing formulas that you may remember from single variable calculus. And the one we'll need is that sine squared theta is 1/2 times 1 minus cosine 2 theta. So we can replace sine squared 3 theta by 1/2 times 1 minus cosine 6 theta. Notice we had to double 3 theta to get 6 theta there. Okay, pulling out the half, we get 3/4. And now this is a pretty simple integral with respect to theta. 1 becomes theta, and cosine 6 theta becomes 1/6 sine 6 theta. Notice there's a small substitution there of u equals 6 theta, so du is 6 d theta, and that's where that extra 1/6 comes from. Now we're going to go ahead and plug in the pi over 3 to get pi over 3 minus 1/6 sine 6 pi over 3. Well, sine 6 pi over 3 is the sine of 2 pi, which is just 0. So we only get the pi over 3. And when we plug in a 0 for theta, we just get 0. So we wind up with 3/4 times pi over 3, which is pi over 4.